In the last lecture, we introduced the notion of buckling failure, where if we have a long, slender column of length L, and we apply a compressive load to that column, then we are interested to know when that load reaches a level at which we get an unstable elastic deformation of this column. It's important to note because buckling failure is an elastic phenomenon. And so we're interested in establishing what the critical load is. And we normalize that by the cross-sectional area of the column, n condition constant times pi squared E divided by L over K squared, where L over K is the slenderness ratio. This is the classic Euler Buckling equation. And if we were to plot the critical load divided by the cross-sectional area, and of course that looks like a stress, against the slenderness ratio, we would get an exponential decay in the critical load as the slenderness ratio increases, and this is the Euler Buckling line. Now, I also mentioned in the last lecture that we also are interested in when that column might yield. It intersects it at the point Q, and then as a first go, we say everything below the yield line and below the Euler Buckling line is safe, meaning loading will not lead to failure, and everything above it is failure. We will either get buckling failure or we would get permanent deformation. So this becomes a failure map because we can locate the geometric and loading conditions for which we have safe loading of the structure. Now, this becomes a little bit more complicated because it is not at all clear what happens in the vicinity of the point Q. So we draw our yield line across here, and we know that there is a region around here where we're not sure is it going to buckle or is it going to yield. Came up with this notion of the Johnson formula to be able to provide a nice parabolic transition from yield to Euler buckling. And we identify that as the point T, and then this parabolic curve ends up becoming our Johnson formula. And everything below the parabolic curve now is safe for loading. Now the problem is we have to find these locations, and the point T is usually found by setting the stress P over A equal to half the yield stress. So we set up a parabolic function and we solve for the constants in that parabolic function. We say that the load, the critical load divided by the cross-sectional area is equal to A minus B times L over K squared. And we identify the L over Ks that are associated with these things. There's L over K Q, and for some reason they call this one L over K1. But L over K1 is associated with the point T. So we go back to this parabolic formula right here, and we realize at L over K equal to 0, P over A is equal to SY, which implies that the constant A is just equal to SY. So we have one of our constants in the parabolic formula. It is simply SY minus B times L over K squared. The other thing we know is that at L over K1, that the critical over A is equal to SY over 2. And so we can then find that by identifying what the L over K1 is. We find L over K1 by realizing that the critical load over the cross-sectional area is C times pi squared E divided by L over K squared. And we know that at L over K1, so L over K squared at position 1 is going to give us C pi squared E SY over 2. And so L over K at position 1 is just going to be equal to twice C pi squared E over the yield strength square root. So that's a relatively easy thing for us then to find. So we go back to this formula up here. We plug in L over K value and solve for B. And if we do that, we find that the constant B is simply the yield strength over 2 pi squared divided by 1 over CE. And this C is the end condition, which varies depending upon whether or not we have pinned or fixed or whatever. So this is the easy way for us to solve the parabolic formula. Once we have that, we know that for L over K greater than L over K1, we use Euler Buckling to find the max loads. And for L over K less than L over K1, we use the parabolic formula. So it's an interesting thing because if you look at the plot, you are moving from a yield-dominated failure to the left of L over K1 to an elastically determined failure to the right of L over K1. When we talk about the secant formula for buckled beams, we are looking at an offset load to a long, slender beam that immediately generates lateral deflection when you apply that load to the beam. So in essence, it's buckled from the get. And so in this case, what we care about is the maximum compressive stress. So the maximum compressive stress in this beam is going to consist of an axial load, which is here, plus the bending load, and the bending load is evaluated at the outermost fiber of the beam. So C is locating the outermost fiber and looking at the bending stresses there and adding the axial stresses to it. So we're adding compressive stresses. So sigma C is a compressive stress. We find the maximum value from an equation that we solved before. We get that maximum compressive stress. Then we set that maximum compressive stress equal to the yield strength in compression, and we solve for the maximum value of P that we can apply to this beam when we have an offset eccentricity of loading E that generates loads high enough to cause yielding at the position of maximum deflection in compression. That is this formula 450. Right here. And when we plotted that formula, we had our original yield strength line, we had our Euler Buckling line, and the secant formula gives values of P over A that look like this. They're asymptotic to the Euler Buckling line, and they move down with what is called the eccentricity ratio. So increasing EC over K squared moves this failure envelope down. At this point, it makes some sense to talk about how you would use a buckling formula to do design. So let's consider Euler buckling. And so we're going to use the Euler buckling equation. We have a load that we want to apply to the system, and we want to size the shaft or the column so that we do not have buckling. So we have a design load for a specified column length, L, and we want to find diameter of a circular column to avoid buckling. What we're going to do is first note that the area for a circular column, so we're looking at circular columns, which is pi d squared over 4. The moment of inertia is pi d to the 4th over 64. And so K, remember, K squared A is going to be equal to the moment of inertia. That means that K squared is going to be equal to the moment of inertia divided by A, which is going to be pi d to the 4th over 64 divided by pi d squared over 4. Well, we can get rid of these pi's. We can get rid of 2 of those. We end up with K squared being equal to d squared times 4 divided by 64, and that just gives me K, the radius of gyration. If I do the math and take the square roots, it's just equal to d over 4. Go back to the buckling equation. You say that here is my design load. We want to make sure that it's not critical. So we're going to take that design load, we're going to divide it by the cross-sectional area and put it into the Euler Buckling equation. And now we're going to express our K in terms of d. So we have that our design load divided by, we're going to put d squared over 4 over here as well, is equal to c pi squared e divided by L, which is another design specification, d over 4, all of that stuff squared. This tells me that my d, if I work it all out, that gives me a shaft diameter, a circular shaft diameter for a specific load over a specific length for a given set of end conditions made out of material where we know the elastic modulus. That's how you would choose the design diameter of the circular shaft. If we were using a rectangular instead of a circular shaft, we would look at the cross section of the rectangular member, and we would have both a height and a width. And you got to realize something here. If I take a column that has a rectangular cross section and I apply a load to that column, a compressive load to that column, it's going to bend in the thin direction, meaning it's going to bend this way before it would bend in the thicker direction, meaning that way. And so there is a preferred direction for bending. So when you are choosing the cross-sectional areas to prevent bending, in this case, you have to write your moment of inertia, I, as 1/12 BH cubed, or in my case, 1/12 WH cubed. That's going to be my smaller moment of inertia. And that's the moment of inertia you want to use in your given buckling formula to determine the height of the beam to prevent buckling. The last structural component we need to talk about when it comes to compressive loading is short, stubby members. So for the simple buckling, Euler buckling, we looked at the critical load over the cross-sectional area. We had the Euler buckling curve, and we have a truncated yield line, and we create the Johnson formula. So as long as we are below this line here and here, we will not have failure of the system in compression. Now, as our L/K ratio moves to the left, we don't have to worry about elastic buckling. We have to worry about yielding. So we're really looking at yield failure when we have short, stubby members. And if it's centrally loaded strut and we're loading it in compression, then the only thing we care about is compressive yield. So that becomes our limit. But what if instead of loading it centrally, we have an offset loading? So what if we have eccentric loading of a strut? Here's the center line. Suppose we apply the load off from center by some amount E. Well, we know that the net compressive stress is going to be an axial compression plus a moment MC over I bending term. So we have axial stress and we have bending stress. And so we need to simply write the bending moment M as P times E. So our compressive stress then that's going to become our maximum allowable is going to be P over A plus P E C over I. Over A, I'm going to multiply by A over A here, which will give us 1 plus EC over K squared. So we can write the compressive stress in that way. And then we simply compare that stress to the compressive yield strength to determine the maximum allowable load. Now, the real problem here is we mentioned the secant formula before. When we have slender beams, so for slender beams, we have to use the secant formula. You go back to the failure map and you say, at what L/K ratio do I have to start using the secant formula? And why does that matter? Because the secant formula drops this stuff down, remember? As the eccentricity ratio increases, EC over K squared, as that increases, you have to lower the allowable loads. It's also important, this eccentricity ratio, the C in these equations where we're talking about yield, is a dimension from the neutral axis to the outermost fiber of the specimen. It is not the geometric correction factor that appears in Euler bending. So keep that in mind. This is a very important distinction. So we have to ask ourselves, at what value of L/K can we just plain ignore the eccentricity ratio? And it turns out that if you solve for the deflection, so the condition to ignore the secant formula, the max lateral deflection, delta max, has to be less than or equal to 1% of the eccentricity. If you use that condition, we find, if we plug into the deflection equation, we find that the L/K ratio, we're going to label this sub 2, is equal to 0.282 AE over P to the 1/2 power, where A is the cross section, E is the elastic modulus, and P is the applied load. So this gives the slenderness ratio for a strut, so you can simply ignore using the secant formula. So if the slenderness ratio is greater than this, if L/K is greater than L/K2, then use the secant formula. If L/K is less than or equal to L/K2, use the simple axial plus bending stress formula given right up here. This is a simple buckling analysis of a rectangular beam that has fixed conditions on the bottom side, free on the loaded end, loaded in compression. Apply the load, and you see that it buckles under the influence of that compressive load. Of course, this is pretty exaggerated deformation, but you get a notion that it will in fact buckle. The bottom side is fixed. It looks just like the fixed free buckling drawings that we saw in our book, that it buckles about the small moment of inertia axis. In this case, it is my x-axis, so the IXX is determining the critical buckling loads, and the smaller buckling loads are associated with the deformation shown.